I said something here. Give me 1 second. I said something here. In many real world situations, the most appropriate deterministic component of a model is not linear. Does that make sense? So for example, many populations of plant or animal tends to grow exponentially. You know that, right? Okay. Now let's say YT, the size of the population at time T. We might employ this model. Okay. This model here, okay, is a population model. I remember uh Matthias' theory of population when he said um population increases in geometric progression while food increases in arithmetic progression. Now, when you take a look at this guy, this is not a linear specification. Why is it not a linear specification? This is not linear in parameter because the parameter here is alpha naught and alpha 1, but exponential now carries alpha 1. That is why it is not linear. But let me tell you this. When I have a non-linear situation, we can actually linearize it by transformation. Does that make sense? Now, if I want to make this guy linear, then I'm going to introduce log. Okay, I'm going to take the logarithm of both sides. When I take the logarithm of both sides, I'm actually going to have this guy, which is going to be log of the response equal to the log of the alpha naught plus alpha 1t plus the error. When you take a look at this guy now, it's like uh uh ln yt now is going to be a new y, and ln alpha naught is a new intercept. When you take a look at that, that's more or less a linear now. So when we have a non-linear situation, and if we're able to linearize it, let me first tell you this. We got two forms of non-linear. Okay, let me say this. Generally speaking, module can be classified into linear and non-linear. Okay, and non-linear can be classified into two, into intrinsically linear. Okay, intrinsically non-linear. What do I mean by intrinsically linear? Intrinsically linear actually means initially it was non-linear, but after using transformation technique, it becomes linear. And when it becomes linear, I'll be able to use a linear approach. Intrinsically non-linear means it cannot be linearized. If it cannot be linearized, then what am I going to do to estimate parameters? Then I'm actually going to resort to numerical method, maybe like Newton-Raphson method of, something that involve algorithm. Does that make sense? Then I'm going to be waiting for the convergence, stuff like that. Okay, now that's what we have. Now, do you know I can also minimize the same way we minimize the original linear model. You take a look at that. The lane T now, minus the deterministic part squared, okay? And use the method of least squared. So when I use the method of least squared, of course, I'm still going to have the same expression that we have the other time, except, take a look at this. Your y in the equation is going to be ln y. Okay, please take notes. Now, I'm going to walk you through an example now. Please, I need you. Now, I need you to look at the difference between the two. Okay, the first one is for the linear model. The second one was initially was a non-linear model, but after transformation became a linear. Then wherever, if you take a look at that now, our x variable is actually time, because we're looking at the population at time t. Time is going to be an explanatory variable, right? So you can see t. Then y is actually going to be ln of y. Does that make sense? Take a look at that. And let me tell you this. My alpha naught is, don't forget in the model, if you take a look at this guy now, we said our new y is going to be ln t. S is still going to be t. But beta naught is ln alpha naught. What am I going to do to get alpha naught? Then my alpha naught is going to be exponential raised to power beta naught. Does that make sense? Because alpha naught is the parameter in the nonlinear module. Beta naught here is the parameter in the linear module. Okay, and if you take a look at the model here after transformation, okay, this is more or less like this is the same as beta naught that we know about plus beta 1 t, okay, plus the error. Okay, so if you want to equate that, your beta naught is ln alpha naught. And don't forget, what am I looking for? Alpha naught. If beta naught equal to ln alpha naught is going to be exponential. You need to exponentiate the other one. And the beta 1 is automatically alpha 1 based on the model specification. And that was how I got that. Okay, now let's go to the example. Okay, we have this model now, right? They gave you this model. This model now. In biological science, it's sometimes possible to relate the weight of an organism to some linear measurements such as length. This is like relating the weight of animal with length. If I know the length, can I predict the weight on average? Now, mathematicians specify that model for us to be able to solve, to estimate the parameters in this model. We actually go to linearize to see. Okay, we introduce a log to both sides. Okay, we got this guy now. Take a look at that. We got this guy now. Then we're now going to equate that guy. We're going to equate what we got, okay, to the conventional model. Okay, here now your beta naught is going to be ln alpha naught. Your beta 1, okay, is actually going to be alpha 1. But in this case, your S would be ln n. At times, when you introduce a log, it could, log could go to the response and log could also go to the explanatory, not all the time, depending on the module specification. Okay, take a look at that. Now, let us go through an example. Okay, in Florida, oh my God, there was a time I watched a documentary and a crocodile was walking on the street in Florida. Okay, so let's take a look at that. Let's assume they specify the model. We linearize. Okay, the model is this. They are relating the weight of alligator compared to the length, and this is the model specification. We introduce a log linearizing for us to be able to use linear model, and this is our data now. Okay, we actually investigate 15 alligator. Okay, the alligator, 15 of them. Okay, but the data that we have, okay, they've already taken the log for us. Does that make sense? So taking the log of L, that is going to be our S. Taking the log of W, that's going to be our Y. Now, since we have X and Y, okay, now the approach that I'm using here, this is a scalar approach. This is not a matrix approach. Okay, now I need to get SSY, SSS, XYY, because if you want to use a scalar approach, there's a formula for beta 1. XXY divided by XSS. That will give us that. Then the beta naught cap is this guy. Okay. Now, after getting the beta naught cap and the beta 1 cap, that is not going to be the final. You now need to go back to the model. Okay. In the model, we said beta naught equal ln alpha naught. For us to be able to get alpha naught, we need to exponentiate beta naught. The alpha naught cap give us that now. And based on the module specification, when we compare with the conventional linear regression, alpha 1 cap equal to beta 1 cap, that is going to remain. Now, if I now want to present my module, okay, I'm not going to present the linearized one. I'm going to present the original specification. In the original specification, take a look at the original specification. Original specification of the module is this guy here. That is the original specification. Okay. All what I'm going to do is to plug in alpha naught and the alpha 1. Okay. Now, when I plug in that, okay, when I plug in that, I'm actually, give me 1 second. When I plug in that, I'm actually going to have this guy. You see that? I've already plugged in. Now, W cap is the same thing as expected value of W. Now, if I know the length of alligator, I can predict on average the weight. I'm done. Is there any question? I'm done. Is there any question? Go ahead. Oh, you mean getting the expression of the formula from the data? Exactly. They will give you original function, whatever function they give you. If it is nonlinear, introduce log to see if it can be expressed in statistical linear model form. Then from there, you're going to have the idea of what your y is, whether you need to lead. But this particular data here, okay, this particular data here, they've already obtained the lane of that and the lane of that. But in the situation where it has not been obtained, then you need to do that. Okay, now I'm actually going to stop my share. And I need you to pay attention now. In the next 15 minutes, I want to do theoretical work. I actually want to, please, I need you to pay attention. Okay? If you don't understand, you know what I want to do now? I want to derive